Okay. All right. All right. So hello, everyone. My name is Lochana Palayangoda. I'm an assistant professor of data science and statistics in Department of Mathematical and Statistical Sciences at University of Nebraska, Omaha. So today my presentation is mainly about my recent research on data-driven optimal experiment design plans for highly reliable products. So let's talk about what is highly reliable products. Is most of the modern products that you see every day, actually, most of them have a very long life. For example, if you have a LED lamp, it has a very, very long life. It's hardly burn out. It's very hardly burn. But the problem of those highly reliable products are their performance depreciate over the time. So that's a problem we have to face. And when you want to estimate the lifetime of those products, we don't really figure out the burnout time. What we are trying to find is how fast they are depreciating or degrades over the time. That's the information we are using to estimate the lifetime of those products. So for example, in this chart, so if let's say my y-axis is a depreciation or the degradation of the product, and the x-axis is the time, and over the time, the depreciation or degradation increase over the time. But the problem is due to the resources in the manufacturers, they don't have all their time to spend live testing those products. They can only test for some of the time, and it's working, but actually due to experimental budget, we have to stop the experiment somewhere here. And then we measure some depreciation or degradation data. And what we are trying to do is that we try to extrapolate and see that how far this is depreciation go. So usually industry specified some threshold level or the standard to say that, hey, if it's reached to this kind of depreciation, let's say 50% of the initial level, and it will categorize as a failure. And as you can see, this time is a random value for product to product. It's different. One product might have it's reached the threshold level, which is maybe 50% of the degradation, maybe at time, let's say 500. Other product might be reached at 700 hours. So this is a variable which is random. So we can find the failure time probability using this set of equations, which I'm not going into details, but you can find the failure time probability of how likely it will fail for a given amount of time. And so you can estimate the lifetime if you know the degradation data. So in this one, what I'm focusing in this research study is that if a scientist comes to me to figure out how much resources that they want to do this experiment. For example, one of the questions they might ask is how many samples I should use, how many measurements I should use, how many time points, what is the time gap between each degradation measurement. So here, for example, I put as a toy example. So here in this experiment, the scientists have used 3 units. You can see that 3 units are here. And for each unit is being measured at four measurements, measurement 1, 2, and 3, and 4. And there are 4 measurements for each unit, which is M is 4. F is the time gap between each measurement. So as you can see, it's a 50 time unit difference is here. So if the scientists know these 3 values exactly, they can easily set up their experiment without a problem. So that's what my my study is about. How can I find the optimal N, optimal M, and optimal F, which is NFM values. If I know these NFM values and sample size, number of measurements, and the time gap, so the scientists can design their experiment effectively. And one of the constraints that these experiments have is that the budget. I mean, they don't have all their money and they can only spend specific amount of money. And there are costs associated with this experiment as well, like cost of operation, measurement, and the unit cost. And we have to make sure that when you want to find this NFM, and we have to make sure that it's within the budget. And so the algorithm that we are usually used in the literature is that when you want to find the optimal design, first we pick what we really want to find from this experiment. Is that the average failure time of the product? Is that the percentile of the average failure time? Is that the median? Whatever the statistic that they are looking for, we have to pick that first. And then what they are doing is that what we can do is that we can find the variance or variability of that measure based on the samples that we have collected. And then we try to minimize that variance such that we find these NFM values. So we minimize the variability of which NFM values, which sample size values, which will give me if I have the minimum variability of my reliability measure, which can be mean or can be variance, it can be median, any variable. So we have to minimize the variance and minimum variance, and within that condition, what are the sample sizes that I can really grab. And here we have to have another constraint we have to consider as well, which is the budget. We have to within the budget all the time. And this algorithm have been designed to accommodate that. And so these are actually using some known distributions, like, they have used parametric distribution, which are when they know the probability distribution, like if they know the Gaussian distribution, if there's another distribution called gamma or inverse Gaussian. So in the literature, what they have done is they have defined a specific probability distribution, and they try to come up with a failure time or these optimal design plans. To how to find NFM values. But the problem is, if you come up with this specific if you define, okay, it follows the specific distribution, it can create some kind of a bias on your selection. It can create a misspecification errors. So in order to accommodate those misspecification errors, what we are proposing here is that use something called non-parametric method, which only data driven. It's only doesn't assume any probability distribution. It's just use the data as it is. So it's a method called saddlepoint approximation. And what we are doing is we just only use the data to obtain the failure time distribution of a product. And we will use this particular product to estimate our optimal design plans and to do that. And these research have been the parametric method, okay, people who use the distribution. So that kind of research they have done for many, many years. Only thing that rare is without using any distribution assumptions, you can create very robust, very strong models because you are not assuming, you don't have a lot of assumptions in your models. So that's what we are trying to do. That's what I'm trying to do here, find the optimal design with this non-parametric method, which I call it as an empirical saddle point approximation, ESA. And here, what I'm doing is that we propose a distribution free or without probability distribution method. And then I run some simulations and show that it's working well, and then apply for applications and then real life applications. And one of the techniques you can use is that if somebody wants to find the mean average of the failure time, so I can use to find the variance of that using non-parametrically, using this set of equations, and then try to find a specific, I wrote an algorithm to find the best sample size for each of them. And then in this algorithm, if somebody wants to find the average failure time, they can find the designs like NFM, which is number of samples, frequency, and number of measurements, and they can design the experiment accordingly. And the next one is if somebody wants to get the percentiles, the algorithm is the same. It's the algorithm has a little bit complications out there. I can explain that if you have any other questions after this session, because it might take a long, it's used like a statistical technique called bootstrapping to find the variance and then find the corresponding NFM values. And then when I do the simulations, I found that this is the, if I compare with the true distribution, that I generated the data from a true distribution and try to find what are the optimal values. And I found that it's the non-parametric method is pretty close. The proposed is the true distributions I created, the algorithms I wrote, which is saying that it's pretty data-driven approach. And so you don't need to assume any distributions to use this novel technique. And it's the same. And then next thing what I did was I apply in real life applications. And in here, I use a popular data set, which is a laser degradation data set. In this degradation data set, I use parametric method, which is when you know the distribution assumptions, and non-parametric method that I propose, which is called the ESA method. And using that method, I try to figure out how they are really performing well. So here we have some kind of a, so these are parametric methods give me NFM as 11, 3, 11, and here non-parametric method will give me 11 to 30, 16. Actually, if you think about here, it's F is the time difference, M is number of measurements. The total experiment time here is like 3 times 11, which is 33, and here 2 times 16 is 32. So they are even there, the numbers are different. If you think about the experimental time and the resources, they are pretty same for all of them. And here it's pretty much same results I'm going to get. So if somebody wants to use this model, and they will have pretty much similar results as the method that they have been currently using. But here we have very less assumptions and pretty robust model. And then what I have done here at last, I developed a distribution free without using any probability distribution. I came across with the optimal design plan for these kind of high-scale experimentals. And then I did simulations and I apply it in real life applications. Feel free to ask if you have any questions. That's all I have. Thanks.